Morning. I'm Spot On Weather Meteorologist Matthew Euler, and welcome to my latest training video. Now, we started the training with basically the atmospheric waves training with long waves. Then, yesterday in part two, we went into short waves. And today, I'm going to cover baroclinic and barotropic systems, low and high pressure systems. So I really hope you get a lot out of this particular training session. I'm going to start the training off by showing you. Now, I did the vorticities part one and part two training videos recently, and as I mentioned, I was trying to find my old hand analysis weather charts. I was able to find the 500 millibar vorticity chart, which I hand analyzed. And then look what's on this particular chart. Okay, we talked about these red X's. See where there's a red X? Whenever there's vorticity maximum, it's going to be represented by the red X's. The solid black line indicates troughing, basically, or shortwave troughs. We also talked about the different color schemes. Let's see, let me find the blue N. Let me see if I can find a blue N somewhere. Yeah, generally the blue N should be here somewhere. I'm trying to find it right now, but unfortunately I can't see much of it. But in general, oh, there's one. Look at this in the Gulf of Mexico, a blue N here at the bottom right-hand side here of this chart. Okay, so we do have some blue N's around Florida as well. So you can kind of get a look at the N's. There is a blue N over central Tennessee as well. All right, so with the 500 millibar vorticity chart, we're looking for maximum vorticity centers, which are represented by these red X's, okay? Then you got your vorticity minimums, the lowest points of vorticity represented by these blue N's. And then you also have the red shading is indicative. When you see red coloring or red shading, that's indicative of positive vorticity advection, PVA. And then NVA is going to be associated with this blue shading. So this is a great example over here in the upper, let's see, this would be the upper left-hand portion of the graphic. This is basically from Montana extending southwestward into southeast Idaho into Nevada. We have this solid black line extending southwestward from this red X, the Vortmax, and that is indicative of a shortwave trough because we're at 500 millibars, so it's a shortwave. And out ahead of the shortwave trough axis, we have the red shading, which is, that's going to be your area positive vorticity advection. So anywhere where you see red shading here, we should be seeing rising vertical air motion. It's an indicator of upward vertical motion in the atmosphere. So there's a good chance if we look beneath some of these red shaded areas, we would see on a surface map some type of precipitation. And anywhere where you see the blue shading, that's indicative of negative vorticity advection, NVA. And if we were to look at a surface weather chart, you would be able to most likely see high pressure or fair weather, no precipitation, no clouds. Additionally, we talked about the XN relationship in the previous vorticity training video. Red X, Vortmax, draw a straight vertical line. Now that line is in green coloring, right down to the blue N, and that is indicative of a jet stream maximum. So if we were to do a jet stream maximum on this chart, for example, I'm looking right here at the XN relationship over Indiana southward to western Kentucky and to western Tennessee. We have the XN relationship here, this green vertical line from X to N. We would probably have some sort of vorticity maximum in this location here on this particular chart. Additionally, you can kind of see my notes here on the right hand side. You got shear lobes with the solid black lines. You got a sawtooth. These sawtooth lines are indicative of these lobes extending from vorticity minimums. The solid black lines are the vorticity lobes, advection lobes, coming down from those vorticity maximum. We also have jet segments on here as well. So it's a very, very busy chart. And believe me, it takes some time to analyze something like this. It really, really does. So as promised, here's your 500 millibar vorticity chart. If we were to look at the 1,000 to 500 millibar thickness chart, now this is really interesting because guess what? This is from the superstorm of March 1993. In fact, you can kind of see the date here in the lower left-hand side of the chart. This is 13 March 1993 at 12 Zulu time frame. And look at all. So what are we looking to really analyze here on a thickness chart, 1,000 to 500 millibar thickness chart? We're looking to analyze for these red areas indicate warm air advection. So warm air is moving into these locations that are in red. And then the blue shading indicates cold air advection. So on a thickness chart, we really are analyzing these thickness lines, these thickness values, and we're trying to determine whether warm or cold air is moving into our area. We also have surface high pressure, surface low pressure is a red L, the surface high pressure is the blue H. This green line, the one I do specially here in green, this is indicative of the 540 decameter line. Now, why is the 540 decameter line, why do we want that to really stand out in this analysis? Well, it's typically the rain-snow line east of the Rocky Mountains. And so anywhere to the west of this green line, if there's any sort of precipitation falling, will most likely be snow. Anywhere to the right of this green 540 decameter line, the precipitation is most likely going to be in the form of rain. The solid black dash lines here are indicative of, these are your thickness lines, and you can see how tightly packed these dash black lines are, these thickness lines are, specifically in the back side of this major, very intense area of low pressure, which is situated at this time at 12Z on 13 March over Georgia. You kind of see a warm front blowing northeast from it, going through southeastern Virginia out to the West Atlantic. You're getting a lot of overrunning precip north of the warm front up here in New England at this point in time. And snow fell as far south as Pensacola, Florida in this particular instance. Mississippi and Alabama got snow. Look where the cold front is, this blue line with these triangles colored in. Look where that is, all the way down into South Florida. This was a doozy of a storm. You really see the 540 line, is this green line here, is all the way down to the northern Gulf of Mexico. So there's a lot of energy in the atmosphere on this particular day based on these hand analysis with all these tight thickness packing lines here. There's a lot of energy going on. Blue again, colder air moving in, cold air advection, red, warm air advection. So I was able to amazingly find these, and I really wanted to show you some hand analysis. I had to do this back when I was going through the meteorology school, and I just wanted to show you what it looks like. All right, so now let's move into today's training topic. We're going to start first with barotropic lows. And there's really two types of barotropic lows. There's a cold barotropic low, and then there's a warm barotropic low. When we look at cold barotropic lows, really the two types that come to mind are what's known as cutoff lows and as well as decaying waves. With warm barotropic lows, we usually look at the heat or the thermal lows over the deserts, and then also tropical cyclones. So what exactly is a barotropic low? All right, it's cold. We look at a cold barotropic low. It's a closed low that exists at the surface with troughing linked all the way up through the atmosphere. And an example of a cold barotropic low would be a cutoff low. Now these cutoff lows are common off Southern California in the spring. I personally have seen what type of weather these cutoff lows can bring. I lived out in California for a bit, and I tell you, it generally will bring showery precipitation, very chilly conditions, lots of clouds, and in some cases with the freezing level lower, you can actually get small hail into California when you have these cutoff lows come ashore. Now they're separated from the main cold air, which is trapped entirely in air that is warmer, so it's south of the polar front jet. Let me draw that up for you here. All right, so you have your main jet stream. Initially it's going to be doing something like this, but over time what happens is the low pressure is going, this trough is so deep like this that it's going to leave an area of low pressure back here to the southwest portion of the trough. This jet stream is then going to reorientate itself north of that low. Okay, so it's going to leave a cutoff low, a closed upper low, cold core in nature. What do we mean by cold core? We mean the coldest temperatures are at the center of this thing. and this is going to be your jet reorientating itself. So you start off with a trough maybe like this here in the top portion, and then this trough gets so deep that the jet stream, because of the curvature, the curved flow here is so sharp, the jet's going to reorientate itself to the north of this closed low. And it's formed in an area where a long wave trough is very elongated, and that's what I was showing you here at the bottom here. We have a very sharp long wave trough. It's elongated, very sharp turning, cyclonic turning here into the base of the trough. Now over time, the jet stream cannot make the sharp turn, and this is where that jet stream is. It's this dashed line here. It's going to reorientate itself to the north of this closed low. So what's going to happen over time is this closed low, okay, you have a low pressure, it's in the upper levels of the atmosphere. Here's your ISO height surrounding it, okay? It's just going to be sitting there spinning for a while until another short wave moves in. We call it the kicker short wave, and it's going to push that cold low finally out. And in some cases, it opens that trough. It basically goes from a closed trough to an open trough again. So this is a short wave kicker here. It eventually picks up the cutoff cold core low, and finally it gets out of your area. All right, so with cutoff lows, this causes the southern portion of the trough to become cut off, kind of like I just showed you on the last slide. The flow splits with the main jet stream to the north of the cutoff low, and sometimes you get these jet fingers which move cyclonically around the low itself. These lows tend to dissipate very, very slowly over time. This is not something that's just going to go away in one day usually, but they may get picked up by that kicker trough, the kicker shortwave, another major trough moving through the region. So we look at some of the diagrams here on the right. What you have in the top diagram we're showing in the vertical is you have lower heights aloft, which makes a lot of sense, right? Because this air is colder, right? This is a cold core barotropic low. It's a cutoff low. So with a colder air aloft, it's going to cause lower heights because it's more dense. The cold air is more dense. So it's going to result in lowering of the upper level heights. Low pressure at near the surface, that happens initially, but eventually over time, the main reflection is going to be aloft, not at the surface. Here's at the surface what you could have initially, where you have these closed isobars, these solid dark lines or lines of equal barometric pressure isobars. You got cold temperatures, -2 Celsius here at the center of this low. And then aloft, right vertically stacked above the surface low. That's the other thing. When we talk about barotropic lows, they're vertically stacked. All right, so you may, I'll go ahead and go over here. Let's see. So let's just say this is the surface, and here's your low pressure at the surface. You go directly above the surface, and that's usually where you're going to find these cold core cutoff lows, okay? Directly above it. So this is what it looks like aloft, though, here on the right. We're showing you a -35 degrees Celsius. Coldest temperature is going to be at the center of this low pressure. You see the cyclonic turning of the winds, these wind barbs here. All right, so you got nice cyclonic turning completely around and circling. These height contours are encircling the closed low. You notice why it's barotropic too? Look at this dashed line, this isotherm. It's completely parallel to the height contours, the solid dark lines. The dashed dark lines are parallel to the solid dark lines. That indicates a barotropic system. Another type of barotropic cold core low is a decaying wave. Frontal systems go through a series of development stages in their life cycle. It's associated with low pressure that begins as a baroclinic low with temperature advection. And when the front occludes, the air mass contrast disappears, and the low pressure will separate itself from the front and become barotropic, moving into the colder air. This usually occurs back to the northwest of the surface low. And it's also found north of the polar front jet stream, and it's going to dissipate over time. So let me show you the progression of this. Initially, you have a surface low pressure area. All right, it's going to stack back to a low pressure, or more specifically, a shortwave trough. So you got this shortwave trough aloft stacked backwards to the northwest of the surface low. And you got the PVA out ahead of the shortwave trough right here. We'll just label it P. That's your PVA. And that's helping to enhance the upward vertical motion and keep this surface low pressure either intensifying or reaching peak intensity Now, over time, what's going to happen is you're going to end up getting an upper level low directly above your surface low because your shortwave trough axis is going to outrun or go faster than the surface low. So let's say that this is your shortwave trough axis here. All your positive vorticity advection now and upper level divergence is ahead of the trough axis at, let's say, 500 millibars. Behind it, you have upper level convergence and NVA, so that's going to result in the column. This atmospheric column is going to fill, and you're going to see that surface low filling first, and that's going to disappear, eventually giving way to this cold core barotropic low. When we talk about barotropic lows that are warm core, we got a couple we need to discuss. We have a close low at the surface, which weakens with height. So with cold core barotropic lows, they actually strengthen with height. But with closed barotropic, warm core barotropic lows, they actually weaken with height. That's a big difference. They're very shallow as well, these warm core barotropic lows. An example we could use is the heat low, or what's known as a thermal low, which is common in the desert southwest of the US, but it can be found in any hot desert environment globally. You get really intense surface heating during the summer, and they're very shallow in nature. They're usually not going to be evident above 850 millibars, which is 5,000 feet above the ground, although there may be a weak reflection still at 700 millibars, up to 10,000 feet, in a very hot arid region, or the western high deserts. These heat or thermal lows do not move, but they just generally seem to stay where they are, and they slowly dissipate and reform. They tend to position themselves over hot spots, so they're always seeking out the hottest surfaces to reposition themselves over. Another type of barotropic low that's warm core meaning that the warmest temperatures are at the center of the system, are tropical cyclones, and we are very much familiar with these. Hurricanes, tropical depressions, tropical storms. They form from the surface upward due to strong convection, vertical rising air motion releasing latent heat to the surrounding air. And that latent heat just keeps acting as a fuel source for the storm. Now, with the warm core barotropic low, with the tropical cyclones specifically, their strongest circulation is near the surface and it weakens with height. And we've all most likely have experienced some sort of tropical system, and you know that it's very, very windy. Even if you haven't experienced a tropical system personally, you know that if you watch the TV reporters, you can see how windy the conditions are with tropical cyclones. There is some upper level support present, but it is not a significant factor in their development. And they move, tropical cyclones move, but can be difficult to pinpoint specific tracks due to weak upper level steering winds. All right, so let's take a look at the warm core barotropic low. A couple characteristics of this feature. You have low pressure at the surface. It tends to weaken with height, so the higher you go up, it weakens with height, the reflection. And what you actually have is, in the case of a warm core barotropic low, the tropical cyclone, you actually have higher heights aloft. Well, why do you think that's the case? Because we have all this warm air in the column. And warm air is going to be more expansive and want to expand as compared to cold air. So you can see the upper level heights rise above these barotropic warm core lows. The vertical depiction shows the area of low pressure. Notice we have a temperature of positive 22 degrees Celsius at the center of this thing. We still have our cyclonic turning of the winds, right like this. And then at 850 millibar, maybe we see the reflection, and the winds are much lighter as these weaken with height. And then you're at 850 millibars, our temperature, let's say, is positive 5 degrees Celsius. So these height contours at 850 completely encircling this low. Notice again, it's barotropic because this dashed line, this isotherm line of equal temperature, is parallel to this solid black line, which is your height contours. So there's no crossing of these dashed lines, no crossing, no angle crossing over of these isotherms with these height contours. Now, with baroclinic lows, on the other hand, these are the major players that create our changeable weather. These are very important systems. They're linked to major shortwave troughs aloft. The trough is going to provide the divergence, that trough aloft, upper level divergence needed above the surface low. It's going to remove mass from the air column and cause the surface pressures to fall. So your low pressure is going to continually get stronger or deepen, and vertically the low and trough axes stack back towards the colder air aloft. Always associated with frontal zones because that's where we have our temperature contrast. So that's really why they're always associated with these fronts. But these are baroclinic lows. We have some sort of temperature advection occurring. Here's how baroclinic lows stack back with height. Baroclinic lows are associated with fronts. All right, so we've got, on this particular surface map, we've got a low pressure represented by the letter L. We have a warm front extending northeastward out of this low pressure. And then we have a cold front extending southwestward. So at the surface, we've got this low pressure associated with these frontal boundaries. Why the fronts? Why does that matter? Because we have air mass contrast. And then as we go with height up vertically, you see how they stack back. See how it stacks back with height? So we can actually, let's just say that this is our 700 millibar level here. We'll label it 700. Let's say this is 700 millibar level. This is our 500 millibar level, right here. And then let's say this is our 300 millibar level. So you see how things stack back towards a colder air aloft above these surface lows. Now the 700 and 500 millibar levels, that's associated with our shortwave troughs. And out ahead of the shortwave trough axis, you've got positive vorticity advection, you've got warm air advection, you got rising air motion, all right? And that is allowing this low pressure at the surface to continually get stronger. And then back here, we have strong upper level winds up at 300 millibars at jet stream level. And if we get that jet streak up there at the 300 millibar level, we break it into 4 quadrants again. Remember, the left front quadrant and the right rear quadrant are the favorable areas for vertical or rising air motion. If you get one of these quadrants, a left front or right rear, directly over this shortwave trough with positive vorticity advection, okay, and then it's all going to feed back down to the surface. Now, baroclinic lows are normally going to form along stationary fronts or weak cold fronts initially. Their most common area for formation is just downstream of the long wave trough axis. So if this was my long wave trough axis, this is my area where I'd expect to see surface low pressure development, okay, for a baroclinic low, right in this area here, downstream of the long wave trough axis. Major shortwave trough is enhanced by the cyclonic curvature of the long wave. So let's say, we get this little shortwave coming through this long wave pattern. It's going to deepen the long wave. The area ahead of the trough axis, this is going to feature the upper level divergence aloft. So ULD, upper level divergence, ahead of the shortwave. Baroclinic low, the surface low movement is accomplished using the long wave pattern and winds aloft. That long wave pattern and those jet stream winds are going to push these baroclinic systems along. The speed of movement is directly related to the speed of the upper level trough. Surface lows follow the long wave pattern. Bottom line. Speed of the low, the baroclinic low, is going to be 70% of the 700 millibar trough speed and 50% of the 500 millibar trough speed. So this is a nice little forecasting rule of thumb. If you were to go up and look at the 500 and the 700 millibar troughs and figure out their speed, the speed of the surface baroclinic low is going to be 70% of the 700 millibar trough speed and 50% of the 500 millibar trough speed. And with baroclinic lows, as far as which direction they go, to determine the direction of movement of surface lows, use the thermal or temperature advection in addition to that long wave, those upper level winds within the long wave pattern. A baroclinic low is going to move toward the region of strongest low-level warm air advection. This low-level warm air advection causes upward vertical motions, resulting in surface pressure falls. Think about it. When we have warmer air moving in with warm air advection, we're decreasing the density of the air column, so the air is going to want to rise much stronger in the vertical, and that's going to help aid in surface pressure falls. It's going to make your baroclinic low much stronger. The low will move to the area of maximum pressure falls following the general pattern of the long wave. We call this the isobaric analysis, isobar lines of equal pressure falls. And wherever you have the steepest or sharpest pressure falls out ahead of these baroclinic lows, that's generally where they're going to go. All right, so take a look at the baroclinic low here. In this case, we have the baroclinic low represented by the letter L. We have our fronts, our cold front and our warm front. And right now it's moving to the east, let's say at 20 knots. All right, it's going to be moving towards the area of strongest pressure falls, and that's right here. So this is where our baroclinic low is going to be moving towards, the direction it's moving towards. Again, notice aloft here at 500 millibars. We're going to use 500 millibars in this example. We have our major shortwave trough. That's this. The trough axis is this very dark line, but this is our trough overall. The major shortwave reflects at the surface of baroclinic low. We have PVA out ahead of this major shortwave trough, so that's the letter P. It's resulting in even more rising air motion here. That's going to deepen or intensify our low pressure. Now, in this case, for speed of movement, we remember we're supposed to take 50% of the 500 millibar wind speeds. So in this case, we're saying the major shortwave at 500 millibar is moving at 40 knots. And that's how we come up with 20 knots down here for the speed of movement on the surface. We're taking 50% of 40, which is 20. All right, so we know the major shortwave trough is moving at the 500 millibar level at 40 knots. Just take 50% or half of that, and that is how fast your baroclinic surface low is moving. Now with barotropic highs, let's switch gears here and talk about these. We have cold barotropic highs, we have warm barotropic highs. Two examples of warm barotropic highs are the subtropical highs as well as cutoff highs. Just like we had cutoff lows, we could actually get cutoff highs. Now barotropic highs, again, I want you to think about this. There's no temperature advection. When you see the word barotropic, no air mass changes. It's vertically stacked, although they may have a slight curve toward warmer temperatures aloft. Barotropic, these barotropic highs are going to be strongest in the upper levels of the atmosphere, and they can form either north or south of the polar front jet. The subtropical high, this is a big one when it comes to the summertime weather in the eastern U.S. Because with the subtropical high, it usually sits at about 30 degrees north latitude, in the vicinity of Bermuda. And on the backside of the subtropical high, we get excessive heat and humidity every summer from it. Specifically, the persistent southerly and southwesterly wind flow is going to keep the temperatures elevated and make it feel uncomfortable in the eastern U.S. on the backside of this thing in the summer. This is known as the subtropical ridge. Another key importance of the subtropical high or the subtropical ridge is it tends to steer tropical cyclones. It really helps determine the orientation of the subtropical ridge, really determines which direction tropical cyclones are coming or moving across the Atlantic. Are they going to go into the U.S., make landfall there, or are they just going to curve right back out to sea? This subtropical high is a continuous belt of high pressure that circles the Earth. It's generally located near 30 degrees latitude, produced by upper level convergence, aloft, downward vertical sinking air motion, and subsidence. So 30 degrees latitude is the magic number when we talk about subtropical highs, and it's a type of barotropic high. Cutoff highs, on the other hand, these are known as blocking highs. Sometimes you'll see the shape omega block with cutoff highs. So sometimes you'll see like this type of pattern here, the omega pattern. All right, that's one type of blocking pattern in the upper levels. Another would be a Rex block, where you have an upper level ridge over a trough. Okay, so this type of blocking high situation is known as a Rex block, R-E-X, and this one is the omega block, shaped like the Greek letter omega. Okay, so these are some big time blocking type situations in the northern hemisphere. You can get these in summer, and you can also get these type of blocking patterns in wintertime. And they definitely keep things locked in place as far as the weather for days. So going back to the cutoff high, it's a region of higher pressure which extends into the higher latitudes, creating a sharp ridge. The polar front jet stream can no longer make the sharp turn and cuts across the base of the ridge in a more direct line. And this is going to form a closed off circulation north of the main polar front jet stream, trapping warmer air around the high in a surrounding area of colder temps. And the omega block can last for weeks in the same area and can cause hot and dry conditions. This one on the right here can last for weeks. And if you're directly beneath this ridge, right in this location, it's going to be hot and dry, potentially up to weeks. Now, I want to draw out how the cutoff high forms really quick for you, so you can kind of get a feel for it. Let's go ahead and erase all this. All right, I want to show you how it forms. Okay. All right, so just like with the cutoff low, let's it's very similar in the way it gets cut off. In this case, though, we have such a high amplitude upper level ridge or high like this. Eventually, what happens is the jet stream can no longer make this turn. It's just too sharp. So what happens is the polar front jet stream, which is represented by this dash line, it cuts beneath the top of this ridge. And what happens is it leaves this anticyclonic closed off circulation, this upper high, to the north of the polar front jet. So the dash line again is your PFJ, your polar front jet. And it has to do with how these upper level winds and the jet stream has to curve around this very tightly curved radius. It just can't make the turn after it gets so sharp. The anticyclonic curvature just becomes too sharp. So the polar front jet stream is going to reform at the base of the ridge. And it's going to leave this closed off warm upper level high there north of the polar front jet. So this is going to be warm air just kind of contained within itself. Baroclinic highs, on the other hand, now these represent our changeable weather across the mid latitudes. Baroclinic highs are linked to major shortwave ridges aloft. So baroclinic to me means two things. Number one, it means we have some sort of temperature change or temperature advection. And number two, it means that we have some sort of connection from the surface all the way up to the upper levels of the atmosphere. Baroclinic highs stack back towards warmer air aloft. They're associated with strong thermal contrast. That's your temperature advection aspect. They most commonly are going to form directly beneath the polar front jet stream. Baroclinic highs, any type of high pressure system, are not going to be associated, do not form along fronts. Here's an example of the baroclinic high on the right. I'll get to that here in a moment, this particular diagram. But baroclinic highs form when the jet stream is going to move across a continental polar, a CP air mass. Remember, continental polar air masses are cold and dry. In the summertime, they're just kind of cooler and drier. But in the winter, they are cold and dry. They come down from Canada into the United States. So these jet stream moves across the continental polar air mass. That air mass is pushed out of its source region by the jet stream. The temperature advection then begins, and you get a surface high pressure system that's going to form at and just downstream from the upper ridge axis, where you have a lot of upper level confluence or upper level converging air, which is adding mass to your column. The air is going to sink. You get cold air aloft, cold air advection aloft as well. Now, there's a couple points I really want to break apart this slide and show you, okay? First, look at the right-hand graphic here that's provided. We have a surface high pressure system represented by this blue area here at the surface. Notice how a baroclinic high is going to stack back. Just like we have with the baroclinic low, there is upper level support. Now, again, we can call this the 300 millibar level here, where we have strong winds aloft. We can call this the 500 millibar level, and then we can call this the 700 millibar level, all right? And notice how it stacks back to the northwest with height. And that's very important, because what do we have going on here at the 700 and 500 millibar levels? We have these shortwave ridges, all right? We have these shortwave ridges. Here's the ridge axis by the sawtooth line. Here's the ridge axis by the sawtooth line. Now, out ahead of the shortwave ridge axis, remember, we've got negative vorticity advection, we have upper level convergence, and we have downward vertical motion right at this location. Downward vertical motion, upper level convergence is going to add mass to the column. The air is going to sink to the surface, and it's going to help enhance our high pressure system there. Now, aloft, you get these strong upper level winds again, but you may get your jet maximum, right? And in this case, we want to be in the right front. So we want to be in this quadrant here, RF, right front quadrant of the jet maximum or jet streak. So we have left front is favorable for storm development, right front, and then we have left rear and right rear. Okay, so in this case, let's say we'll put this RR right rear quadrant of the jet maximum or jet streak. Okay, so in this case, let's say we have the right front quadrant of the jet max right over our location in association with a shortwave ridge at 500 and a shortwave ridge at 700 millibars. It's all connected here. We have upper level convergence of air in the right front quadrant of the jet max. We have upper level convergence and negative vorticity advection ahead of our shortwave ridges at 500 and 700. Everything is connected three-dimensionally and vertical, okay, in the atmosphere. The other thing I want to mention and draw out is right here, this last bullet here. The surface high will generally form at and just downstream from the upper long wave ridge axis. So let's do this, okay? This is our upper level ridge axis. This is our long wave. You're going to get a surface high that is generally going to form right in here, okay? Because this is our ridge axis here. All right, so this is our surface high pressure system. It's going to form at and just downstream of this long wave ridge axis. And why? Because we have confluence of air, and that's going to help add mass to the column and build and cause the surface pressures to rise. So baroclinic highs follow the long wave pattern. They tend to move toward areas of cold air advection than the low levels. The cold air advection causes the surface pressures to rise because the air is more dense, and the high is going to move to the area of maximum pressure rises. So with baroclinic lows, we said that they generally follow the long wave pattern of the baroclinic lows, and they move toward areas of warm air advection. Baroclinic lows also are going to move towards areas of maximum pressure falls. With baroclinic highs, it's the opposite. Baroclinic highs move toward areas of cold air advection in the low levels and towards areas of maximum pressure rises. Again, you could look at an isobaric analysis to look at the isobars, those lines of equal pressure rise and fall, and determine where are those rises and pressure fall, those pressure rises and pressure falls the strongest. Baroclinic highs move toward the equatorward, southward, come out of Canada typically towards the southeast. The speed of baroclinic highs can be estimated by using 60 to 75% of the 700 millibar wind speeds. All right, so that wraps up the training. Wow, there was a lot this morning, wasn't there? Okay, so we talked about, I started things off by showing you my 500 millibar vorticity chart, kind of explaining vorticity, what it looks like on that type of chart, what the different coloring and what the letters mean. All right. We then went into the example of my hand analysis thickness chart, kind of showing you what we're looking for on the 1,000 to 500 millibar thickness. We're looking for areas of warm and cold air advection. We have our surface pressure features labeled on there as well, the highs and lows. Then we went into talking about barotropic and baroclinic high and low pressure systems. All right, so the training summary: deepening of long wave troughs, cold air advection, and diffluence associated with shortwave troughs. All right, so what are we saying here? If you want to deepen your long wave trough, you want to have cold air advection coming into that base of that long wave trough, and you want diffluent wind flow in the upper levels of the atmosphere. That's going to allow for the removal of mass aloft in the air column. And that is typically going to be associated with shortwave troughs. Filling of long wave troughs, what do you need? For long wave troughs to fill or weaken, kind of level off, you want warm air advection and confluence aloft associated with shortwave ridges. Building of long wave ridges, we generally are looking for warm air advection and converging air aloft, adding mass to the column. It's associated with shortwave ridges. And then weakening of long wave ridges, we want cold air advection, colder air coming into that long wave ridge, and you want diffluent winds aloft, which is going to remove the mass. Ridges, in order to get stronger, want warmer air coming into them, and they also want confluence or converging air in the upper levels of the atmosphere to add mass. Major shortwave features such as the shortwave ridges and shortwave troughs are going to follow the long wave pattern. Barotropic systems, by the way, have no temperature advection, while baroclinic systems do have temperature advection. Baroclinic lows are going to be supported by these major shortwave troughs aloft, while baroclinic highs are supported by major shortwave ridges aloft. That is all I've got, everybody. This was an action-packed training video. I tell you, but these are such key principles. Baroclinic and barotropic systems, I mean, this is like, if you can really get this down, these concepts down, you really will understand how a weather map really sets up with the different types of features on it. But yeah, that's all I got. If you want to leave me some feedback, please feel free to do so here. I thank you so much for subscribing to the Spot on Weather YouTube channel. By the way, it's now September 1st, so hello fall. Meteorological fall is upon us, folks. So very exciting there that we're heading into the fall season. It's such an enjoyable season. We get rid of the heat and humidity of the summer, which is just a nice relief. And then we start seeing some of those leaves change on the trees. I've got a couple more videos lined up. I've got one on system intensity. I've got wave cyclone process after that video. And then I've got where we find the heaviest rain and snow and what are some of the synoptic patterns that produce the heaviest rain and snow. And then finally, I've got another one just waiting in the wings, another video, and it's really going to be really covering the La Nina winters. What kind of temperature did we have for La Nina winters? What type of precip anomalies do we have with La Nina winters? What did the 500 millibar level look like for La Nina winters? I've got that lined up. I've got some great examples to share with you from those past winters. So I've got a lot to cover. I'm trying to get caught up here. And you know, this life kind of moves at you, and so you got a lot of things going on at the same time. So I try to cut these videos when I have the availability, and I certainly hope you enjoy these presentations. That's all I got for now, everybody. Have a blessed Sunday. Enjoy the rest of this holiday weekend if you're fortunate enough to have Monday, Labor Day, off tomorrow. All right, take care, everybody. Until next time, God bless.